So you guys are the few like marathoners. Last session still going strong. So we'll try to kind of get this going soon. This topic, we've been, it was kind of introduced in last minute, and with me is Bryan Cutler. So we're the co-presenters for this particular session. The topic is obviously like optimizing your SparkML pipelines, but before going into that, I thought we'd talk a little bit about what we're doing in general in this space. So my name is Vijay Bomreddy-Pally. I manage something called the Center for Open Source Data and AI Technologies, which is a mouthful, or we call it CODE for short. It stands for Coder in French. We were previously known as the Spark Technology Center. And with me is Bryan. Bryan, why don't you?
I'm Bryan Cutler. I'm a software engineer at IBM, and I'm a committer for Apache Spark and Apache Arrow. I do most of my work in open source software, and I have a focus on Python and machine learning areas. There's my handle on GitHub, too. Feel free to contact me for any questions or pull requests on the material.
Thanks, Bryan. And so the topic I thought what we'd do is we'll talk a little bit about what IBM's doing in open source. We'll quickly deep dive into what we call the AI lifecycle, specifically what we're doing, the open source projects we are championing as part of this. Then we'll deep dive into model tuning in Spark. That's the portion that Bryan will cover. And then we'll also go into PySpark Vectorized UDFs, right? That's the main topic of this session. And then we'll pop back up and we'll do some Q&A, right? So that's what we're going to do. Since it's the last topic of this conference, I thought I'd start with a little bit of trivia. So IBM has a long history of AI, right? I mean, we've been at it for quite some time, but how many of you knew that we were like the technical advisor for 2001: A Space Odyssey? Actually, how many of you know about the film, the Stanley Kubrick classic film? Okay, good. A lot of sci-fi people in the audience. We were the technical advisor, and I mentioned this story earlier as well, but Stanley Kubrick asked his producer, he's like, does IBM know that this is about a psychotic computer? And the producer said, yeah, no, they know. It's as long as it's not associated with their name or something, they're okay with it. So fast forward to 97, IBM did Deep Blue and very famously beat Garry Kasparov, right? And that time, it was a major advancement in technology and the things that we had to do in order to get there. And fast forward to 2011, everyone familiar with Jeopardy? And IBM's, Watson machine that beat the winningest champions in Jeopardy. So from that time onwards, things went into warp speed in open source, right? So Google did Go, and every day there's some university publishing papers where things are being bettered, things are reaching superhuman performance in deep learning and AI, right? Deep learning is an area where this is going through a massive renaissance. So, when we looked at this, we've been very active in the Spark ecosystem. So we were known as the Spark Technology Center. Whenever IBM deems a technology very foundational, things that are very, very relevant to like the industry, we pulled together a center of excellence, and that's what the Spark Technology Center was, to do things around the Spark ecosystem. And we've been working very closely with Hortonworks, Databricks, Cloudera, and everybody in the community. Even, in many of these cases, we compete with them. But we also work very openly in the community because we want to make sure Spark is very viable for enterprise, for them to leverage this. And we don't always work on the coolest pieces as well. We also go and get Kerberos done. We get things that are absolutely needed for enterprises to be able to run Spark. And so, over the last year, we expanded into deep learning. We expanded into other areas. So how does TensorFlow interface with Spark, as an example? Bryan hopefully will just briefly touch upon his ideas over there. The bottom line is we are doing a lot of work in order to enable that entire life cycle, right? And this is what we're known as, the Center for Open Source Data and AI Technologies. Everything that we do is out in open source, so I would highly recommend you check out the projects over there, and please reach out, and we can collaborate out in open source. As I mentioned, it's a relaunch of the Spark Technology Center. Very briefly, just one slide of chest thumping, and I promise I'll stop after that, is we have a lot of committers in the Apache ecosystem. We've contributed almost 55, it's close to 60,000 lines of code into Apache Spark itself, but we're also working in about 10 different projects around it. So Apache Arrow is an example. Bryan has done a lot of work in that, and we'll talk a little bit about how that is relevant. Within IBM, just so you guys, for those of you who are building on top of Spark, IBM has built about 25 different product lines on top of Spark. Right? So this is not something that we take lightly. Major product lines like Watson Studio, a lot of the Watson engine is built on top of Spark. Right? And it is the scale-out infrastructure. Right? So we're constantly enhancing it. So these product lines itself are a huge source of our roadmap, and we do this work out in the open. So everything that you see is done in Apache Spark, right? So as an example, our SQL team right now is putting data federation capabilities, predicate pushdown capabilities. Bryan will talk about his work with PySpark UDFs, right? So all of this work is being done out in the open. As we looked at where we wanted to go next, right, we wanted to kind of relaunch the center in the context of the work that we're doing. As I mentioned, we're doing a lot of work in deep learning as well. So we relaunched the center. We're calling it Code. And everything that we do it in the context of IBM code. So just Google for IBM code, and everything open source of IBM will show up. Deep diving specifically into what we're doing on the data and AI lifecycle, I want to focus your attention briefly on this. Right? It's a grossly simplified lifecycle, just for the purpose of understanding. But at a high level, if you think of what we do in AI, like an end-to-end story perspective, is you're using data, applying machine learning to automate decisions. Right? That's what we're doing. Everyone is trying to kind of infuse more and more. We say AI, but what is it? Right now, the techniques are machine learning, deep learning, right? And we're pushing more into reasoning systems and things like that. But this is where all the action is right now. Oh, sorry about that. I didn't realize this didn't go all the way to the back. Everything okay? Sorry about that. Wow, I wonder how many other people did that. So bottom line is, so we are continuing our work in Apache Spark, right? So there's absolutely continued involvement in Apache Spark. As I mentioned, we're looking at more at Keras, TensorFlow, PyTorch. The reason is because our enterprise clients are going there, right? They want to kind of apply these deep learning techniques. They want to go in and they want to, and they're starting off sometimes with smaller steps, like what we've done with our Watson visual recognition, where they're saying, hey, I have a bunch of engine damage pictures. How do I classify them, right? And when they're doing that, they're saying that these open source frameworks do not have what they need in some cases. So we go in and we enhance these frameworks, right? So that's how we're looking at this. We recently launched something called the Model Asset Exchange, right? The Model Asset Exchange, when a deep learning engine, or like someone wants to leverage deep learning, there are a few models who's out there, but these models are not readily usable. Right? So we're going in there and we're curating these deep learning models. We're doing this for PySpark, PyTorch, Keras, TensorFlow, all these different frameworks. We're curating canonical models and we're putting it out there. Right? So I highly recommend checking out IBM Model Asset Exchange, where you can go in, everything's available. You can just download it as Docker images. The training data sets where we can make it available, we are making it available. Or in some cases, you can actually retrain them using some of our Watson pipelines, right? But everything is out in open source here, right? We also launched something called Fabric for deep learning, and I'll talk a little bit about that. And in Spark, we're also, how many of you, like in production, use PMML or heard of PFA or MLeap? So this is for model serialization, right? You want to kind of not necessarily have Spark on the inferencing side as well, right? So we've done a lot of work. We recently launched a project called Project Aardvark, right, with PFA in the middle, right? We wanted to kind of add to the Hadoop Animal Zoo, right? So we decided to launch the Anteater project as well. In addition to that, we're also doing work in the Jupyter space. So those of you who are using Jupyter and would like to deploy it in your enterprise, there is work needed to be done in order to make the single-user system like Jupyter, right, interface with a multi-user system like Spark in a highly parallelized multi-tenant way. So what I mean by that, if you're kind of routing all of these kernels through one machine, there's a major bottleneck that happens, and pretty soon your data scientists will leave a notebook open, you will have a kernel occupy some memory, and next thing you know, new data scientists will not be able to log on to the system. Right? So we've done work with Jupyter Enterprise Gateway such that we allow for kernel remoting. Right? So Apache Tori is the Scalar kernel. That is allowed to run on Yarn as one of the containers in Yarn. We've also extended that to Kubernetes. So we're doing work in the Jupyter space as well as in Pandas and scikit-learn as well. Right? So, you know, I mentioned briefly Fabric for deep learning. That is an end-to-end fabric that we're putting together that not just works with TensorFlow and PyTorch, but like 5 different deep learning frameworks. And it provides for data scientists a consistent way to kind of train, deploy, inference, right? Train, deploy, and serve using this one fabric. Right? It is a consistent API that we provide, and then your deep learning scientists can work with PyTorch, Keras, TensorFlow, all these different frameworks, and it is one unifying framework that we're putting together. Right now, we partnered with Selden. How many of you are familiar with Selden Core? Right? It is a way to serve deep learning models. We're also kind of completing that whole story so that everything that we're doing with regards to AI ops happens in open source. Right? So please keep an eye out. Go to codait.org, codait.org, and you'll find details on all these projects. I mentioned briefly about Jupyter Enterprise Gateway. For those of you who are looking to deploy Jupyter going against Spark, this is a project that we're actively working on. And as I mentioned, the ability to run kernels on your cluster remotely is a huge advantage, because then that way you can take advantage of your full cluster. Right? In addition to that, we are also enabling user impersonation end-to-end. We're also enabling, essentially think of it as a scale-out mechanism for running your Jupyter notebooks. No, boom is like just basically saying that when you run too many kernels on that one node, eventually you'll run out of memory. No, we don't want to name a project boom. Doesn't give the right message. So, but no, this particular slide is just saying that, if you keep adding more and more kernels to one gateway node, eventually you're going to run out of memory, and your cluster is going to have a lot of resources available, but you're not going to be able to actually onboard new data scientists. What do data scientists do? They run their notebook, and at the end of the day, or even middle of the day, they're like, leave it open, and they go away. That holds on to the memory, right? And then you have more and more kernels. So we're also working on gracefully paging out kernels as well, right? So all of this work is being done in the context of the Jupyter Enterprise Gateway, right? It is truly that, which is taking the Jupyter project, which is amazing, a notebook project, and making it available to an enterprise cluster, right? That's what it is, right? And you can read all about it out in the IBM Code. IBM Code website, we have everything out in the open. We continue our phenomenal amount of code contributions that we've done in Spark. And the reason we continue that is, as I mentioned, it is very, very important to IBM, right, that we continue improving Spark. The products, I've listed some of these. The products are not that important in this discussion. What I wanted to make sure you understand is that our contributions, and if you just go to jiras.spark.tc, you will find a lot of contributions, our live dashboard into what all we're contributing there. And today's talk is going to be about some of these contributions that we've done. So turning back to this, right? This is the life cycle that I presented. I mentioned some of these projects. This particular talk, we wanted to focus on 2 aspects. One is what we're doing in Apache Spark itself with regards to Arrow integration, right? How we've kind of enabled that so that we can enable, for the Python developers, we care about Python developers a lot. How do you speed up their interaction with Spark? Because Spark being like a JVM-based. Prior to us doing this, this was a problem that was highlighted by a number of architects within IBM, because when we were putting our data science projects, we saw Spark, Python being used a lot, but when they needed to scale out into Spark, this was a challenge, right? So that's why we embarked on this project. And the second thing that Bryan's going to talk about is about ML tuning itself using SparkML, right? So for the rest of the talk, we're going to deep dive into these 2 particular aspects, and then we're going to pop back up for questions, all right? So, Bryan, all yours.
Thanks, Vijay.
I'll try not to fall off the stage. I'm just going to stand here.
OK, so first I'm going to talk about model tuning in Spark and cover 2 different topics about how to scale up with an existing feature in Spark 2.3, and then some ongoing research that we've been doing in optimizing this for pipelines. The second part is going to focus on PySpark Vectorized UDFs, also called Pandas UDFs. And I'll talk a little bit about how we're using Apache Arrow and Spark, and show you how to convert your Pandas UDF into a pipeline that you can use in your SparkML framework. So starting off with model tuning in Spark, this is where you want to scale up your model tuning to select the best model possible. This is maybe your standard ML workflow. There's a number of different processes. We're going to focus on model selection, and this involves taking a large number of candidate models, and you're going to need to train each one and evaluate through different hyperparameters and get a metric, and then use that to kind of select your best model and choose that as your final model. So as we walk through some of these examples, I'm going to be using this example pipeline. It has 3 stages, tokenizer, count vectorizer, and logistic regression. Tokenizer is just a transform, and count vectorizer and logistic regression require training models. And each one we have a couple of different hyperparameters to choose from, and we have 2 values for each of these hyperparameters. And so the goal of our model selection is to fit this best pipeline model, which is a combination of all 3 stages, and choose the best one according to some metric. So this is how you would set things up in Spark. You would define your pipeline. It doesn't work. But okay, at the top, you're defining your pipeline stages, and then you follow that up with defining your parameter grid, which includes the hyperparameters that you want to search for in your model selection. And then you would choose some form of evaluation. Here we're going to be focusing on cross-validation. And the features that I'm going to talk about are also available in the chain validation split as well in Spark. So since we are focusing on 2 hyperparameters with 2 values, that leaves us with 4 possible candidate models to select from. And the way Spark works in this case is it takes each model one by one, trains it, evaluates it, gets a metric, and then goes on to the next model. So it's a sequential process. And it does each one until all 4 of these are going to be evaluated. So as we start adding more and more hyperparameters that we want to search for and adding more stages to our pipeline, we can easily end up racking up on all kinds of different models that we need to evaluate. And this makes cross-validation really expensive. And the problem is, if you're not utilizing every available resource in your cluster, since this is a sequential process in Spark by default, any resource that you're wasting in your cluster is just going to be compounded for every single model that you end up training. So it ends up being a huge, long, involved process. So one way to combat this is to make sure that the Spark scheduler has plenty of jobs in queue to keep all the resources available and take advantage and fully utilize the cluster that's available. So to do this, we introduced in Spark 2.3 a new parameter that's new parameter that's available in cross-validator and chain validated split called parallelism. So this is a number that governs the maximum amount of models that can be trained at once. So you use it just by setting parallelism to your specified value. And now let's take a look at how this works since we set this value to 2. We'll end up queuing 2 models to be trained and evaluated at one given time. So it'll go through the first and second pipeline models at the same time. And once those are done, it continues to do the next 2. So it's no longer just a sequential process with waiting. You're able to send more and more work to the Spark scheduler. Okay, the way this is implemented is using wrapping the fit and evaluation process in a future. And this is done at each fold during cross-validation. So at the end of each fold, they're synchronized up, which acts kind of like a barrier to prevent excess caching of your data sets. Some things we considered about the implementation is we needed to define a dedicated thread pool so that it is able to run without deadlocking with the default thread pool using parallel collections. And we enabled a more flexible execution context that could be possible to set from different areas in the future and maybe automate the process of choosing a value of the parallelism. So we ran some performance tests and compared running cross-validation in parallel to the default of serial and varied the number of data samples. We used just a simple logistic regression and had a parameter grid size of 12. And we measured the elapsed time to complete the cross-validation. So here we set the parallelism to 3, and we had a standalone cluster with 30 cores total. And we partitioned the data into 10 different partitions. So we ended up seeing about a 2.4 times speedup, which kind of makes sense since we set the value to 3. We didn't quite get to that maximum value, but fairly close. And you can see as we increase the number of data samples, it roughly remains a constant time speedup. So some best practices for using this, since it's just a single integer for now, it's kind of hard to know exactly what to set this. If you set it too low, you might end up underutilizing your resources. Too high, you could overload some memory or other cluster resources. But a good rule of thumb, if you know the number of cores in your cluster and your partitions, then you can just divide those and come up with an integer. But for a mid-size cluster, a good rule of thumb is maybe just keeping this value somewhere under 10. OK, now I'll talk about optimizing this process for using pipeline models. This is some ongoing work that we're doing. It's not in Spark yet, but hopefully it'll get there. So your typical Spark pipeline is going to be multiple stages and fairly complex. And you'll end up having a parameter grid with a lot of different parameters from different stages. So as we saw, we end up with a huge number of possible candidates to choose from. And we also saw that model parallelism can help, but we can actually do more optimization with a pipeline to make this even better. So the problem is Spark treats each pipeline model completely independently, which is easy to do in parallel like before. But the problem is we end up duplicating a lot of work. So depending on how you set up your pipeline and your parameter grid, you might end up fitting the same model multiple times or doing the same kind of transformation over and over again. So a better way to represent this is with a graph. Just going back, let me talk about what work is duplicated here. You can see that for the count vectorizer model, we need to fit 2 count vectorizer models, but we end up doing each one twice. And we have a tokenizer at the beginning stage, so we end up doing the same tokenizer transform 4 times. So representing this as a graph in the form of a tree, we can have each node represent an estimator or transformer with a specific set of hyperparameters. And a path into the graph from the root to a leaf represents a single pipeline model. I'll walk through a sample of how this is going to be executed. And this can also use the parallelism parameter that we talked about before. So we'll set that to 2. Since tokenizer is just a transform, we begin by fitting the 2 count vectorizer models. once these are fit, we'll begin to transform, and we can actually cache the result of that count vectorizer transform and start to fit our first two logistic regression models. Now, once all the child tasks are done from a cached node, we can go ahead and unpersist that node. And so we'll do that here, and then proceed to fit the next two logistic regression models. And eventually, we have all our models fit, and we'll move on to the evaluation stage, which is run pretty much the same way. Only now the count vectorizer model is a transform, so we begin by evaluating the logistic regression models. And once again, we can cache our intermediate result of the count vectorizer model and unpersist it when it's done. So we wind up computing metrics for each fold of the cross-validation. And after each fold, we average these together, and we can use that to select the best model, which is highlighted in green here. So using this feature, we also ran some performance tests, and we compared this against the standard Spark cross-validator with this parallelism parameter enabled. This time, we varied the size of our parameter grid from 36 to 80 models, and we kept the data size constant. We also used a standalone cluster with 30 cores and parallelism 2.3. So here we saw up to a 3.25 times speed up. And we noticed that as our grid increased and we added more and more models to be evaluated, the speed up increased. So this actually gets better the more complex your pipeline gets. You can check out this work with the following link. It's still in an experimental stage, so not quite ready for production. But if you're interested in this, check out the JIRA that's at Spark 19071, and help comment and push that through. OK, now I'm going to switch gears a little bit and talk about some work I've done in PySpark using vectorized UDFs, also called Pandas UDFs, and talk about a little bit about Apache Arrow and the big data ecosystem. So first, a little bit about Python and big data. Looking at Spark, one reason why it's so successful is it was able to integrate a lot of different tools that traditionally require completely separate systems. So in the same framework, you can do SQL queries and launch your machine learning tasks. And it also has a pretty mature and stable Python API. Now, most big data tools are based on the JVM, but we've seen more and more people using Python for analytics and machine learning, and they want to take the work they're doing on a single node and be able to scale that up with Spark and still get the same performance from Python as you'd see from using a pure JVM application. So the question is, how do we connect these Python programs to the rest of the big data ecosystem? We end up doing a lot of different things, like pickling the Python data, using JSON, XML, strings, writing to files. And this ends up in a lot of specialized work in each system in order to handle transferring the data back and forth. And it creates a lot of serialization and data copying, so it ends up being really inefficient and hard to debug problems because there's no standard. So a little bit about the architecture of PySpark, which is the Python interface in Spark. It provides a wrapper around the Spark JVM. And in your driver application, it uses py4j to run your JVM commands. And on workers, a JVM is started, which kicks off a Python process to do the work. When data needs to be transferred to and from, it's always done in the pickle format, which ends up causing a double serialization cost as you transfer data to and from your Python and Java processes. So Spark introduced the DataFrame API, and the good thing about this is you can actually avoid these serialization issues and completely run your application in the JVM. And this lets you achieve performance that's almost as good as using pure Scala or in Java. But the problem is if you end up running any kind of custom Python code, you wind up going back to these costly serialization problems. So just a few details about the Python worker. You can see that the driver uses Py4j or a socket to talk to the JVM, and that JVM talks to the worker JVMs, which then pipe data back and forth between the Python processes. So let's look at a word count example using the DataFrame API. This is Python code, and it makes use of these built-in functions that are highlighted in blue, split and explode. And so by doing this, we end up keeping all work done on the JVM. So it's really fast and efficient, and everything's great. But then we run into a problem. Like, let's say your tokenization needs to support different languages, and your built-in function to split the text is no longer going to cut it by splitting on a single character. So you have a couple options. What you can do is have your Python user write some Scala code to implement a new function that does the work, or you can go back to using your custom Python code. But then we have these performance problems. So we really need a way to fix these serialization issues and make things efficient. Okay, just a little bit about Apache Arrow. That is brought on in Spark in order to help with these issues. Apache Arrow is a standard data format that's used to transfer data between systems. The format itself is language agnostic, so it has key implementations in libraries like Java, C++, and Python. The Arrow format is optimized for fast data processing, and it can help avoid these serialization issues and uses efficiently chunked data arrays. So this is currently being used internally in Spark to help transfer data between the JVM and a Python process. And it's particularly useful for helping with Python UDFs, also Pandas UDFs. Okay, I'm going to just go ahead and skip that. Arrow is still maturing, but in the past year, adoption has been increasing really rapidly, and a lot of different systems and companies are using it. So just a quick example of a Python UDF. This isn't really doing much. We're just adding one here, but it's actually interesting the way that Spark evaluates this. Using the input variable x, Spark will pass in a pandas series as a value. So when we perform this addition operation, pandas is going to go ahead and execute this very efficiently, making use of hardware acceleration and SIMD operations to quickly compute a result that's also pandas that it can send back to Spark to be evaluated. So looking in detail of what a Python worker looks with and without Arrow. Without Arrow, the JVM ends up having to pickle all the data and each individual scalar value and then pass to Python, where it can then be deserialized. And record by record, the UDF supplied, you get a result, and you repeat that over and over again until you complete the records, and then you send it back in the same way. Now, a worker with Arrow is much simpler and efficient. The JVM can go ahead and make a Arrow batch directly, which avoids any kind of data serialization. This can be sent to Python, where it's easily consumed, and then apply Pandas to process the data and send it back again as an Arrow record batch. So this process can have a huge impact on your performance. Obviously, it kind of depends on what your UDF is doing and what kind of data you're transferring back and forth. But even with our simple +1 example, you can see we achieved over a 3 times speed up. So going back to our tokenization problems, now this makes it possible to use an existing Python package called Spacey to perform our tokenization. So all we really need to do is wrap Spacey in this UDF using Pandas. So here our input series is a series of documents, and we use Pandas to apply the Spacey tokenizer to each document and return a Pandas series of string arrays. And this makes it really easy to configure language. Taking this tokenizer with some boilerplate code, you can go ahead and wrap that up into a Spark pipeline. But it's not always easy, and it can be difficult to play with the rest of the Spark machine learning framework. So you might, if you end up doing this, you might want to check out this open source project called SparkML. It's a library extension to Spark and lets you add additional estimator or transforms. And you can easily write your own Python code that fits nicely within the rest of the SparkML. And it already has this Spacey tokenizer that we talked about built in. So doing that, we can then build our text classification pipeline and connect that with the rest of Spark. So we can feed it with Spark SQL and get the output, get our pipeline model and tune it with the existing Spark cross-validation. All right, so do we have time to go over this?
Very briefly. So I think, so hopefully this gives you a flavor of why we're doing some of this work. So just to kind of give you an idea, this problem came about, especially the Arrow work. We've had teams come back to us and say, hey, we wrote this whole thing in Python, and our initial response to them was, okay, you may have to rewrite it in Scala if you really want performance, right? So when we looked at like how much developers want to use Python, we said, okay, let's see if we can kind of improve that performance a little bit. And this was a culmination of almost a year and a half worth of work. So lots of different projects going on, as I showed you in that life cycle. Please go ahead and check out some of the projects. And one last bit is I wanted to talk a little bit about IBM issued something called Call for Code, right? And we're trying to pull together disaster mitigation solutions, you know, and there's a huge award for that. There's, I think the first prize is close to $200,000. And you know, everyone's open to participate. You can go out to Call for Code, the website. We've partnered with the UNHCR, right, for the Red Cross. We've also participated, you know, we've partnered with the Linux Foundation. The Linux Foundation folks will themselves, and I believe, you know, Linus Torvalds is going to also be involved in the code review. But he's promised not to be very, very thorough as core as he is with the Linux kernel, right? So please go to Call for Code and check out what you can do, right? This is something that we don't believe is for someone else. One of my team members was actually impacted by the fires up in the North Bay in Santa Rosa. So, you know, and one of the things that he told me was, you know, it would have been nice if he got a warning at least 20 minutes before as opposed to 2 minutes that they got. They literally had people banging on their doors and say, get out of the house, right? So these are the kind of things that we can do. You know, please go to Call for Code. And like I said, it's a great experience. You know, there's possibilities to actually productize it. We've partnered with some VCs. You will have access to some of the winning selected solutions. Will have partners with VCs, so you can actually productize this. That's all. I don't know if you have any questions, and if there's any time for questions, actually.
Yeah, I think we're out of time, but...
Can you summarize the question?
Sorry, I couldn't quite hear all of that. Is it possible to use the mic, or we can talk afterwards if we're out of time?
Yeah, we can talk about what our current advice is based on the implementation of Spark. I think your question is basically like you're going through the same process, which is people are implementing things in Python, you're having the production issue challenges. How do we get there?
Yeah, so
right.
they basically open PySpark sessions and then they forget to delete or close it.
Okay, so so that is a different issue. So that if you're talking about like Python kernels occupying memory in your cluster, we can talk about that offline. So Jupyter Enterprise Gateway, one of the pieces of work that we've done over there is what we call graceful culling of kernels, right? It's such a way that we retake the memory that these kernels with, there's a timeout there's different schemes you can use. So we can talk a little bit about that. So, but yeah, Jupyter Enterprise Gateway would be the project, but we can talk a little more offline.
It's a little bit more towards the latter, but it's actually like probably pretty more simple than that. We're basically just saying, we have a list of possible candidates we need to evaluate. Instead of just doing one by one, which one gets into the Spark scheduler at a time, we're just enabling it to send more than one. So Spark goes ahead and handles the job and tasks scheduling of those models, and we just synchronize getting them back and evaluate them just the same way. So it's not doing anything like fancy under the hood, except allowing more jobs to be scheduled and better utilizing your cluster then. Yeah.
But to your question about how does a data scientist specify multiple parameter ranges and things like that, there's a separate project we're doing to improve the notebook interfacing with deep learning jobs. So we're doing this in the context of deep learning. But that project we haven't yet it's in the process of being open sourced. So we'll, once that is out there, we can talk about like what.
Well, so I went through the TensorFlow that point.
So if you don't mind, so there are two aspects to that. Right? One is the user specifying what parameters they want to do, and one is monitoring what the output of that is and redoing that. The latter part is, I don't know of anything out in open source that does that, but.
Definitely
It's my idea, so don't steal it.
Well, it's a known problem. So that's another thing that, the team, when I mentioned the notebook where you can specify ranges and the team is working on that project is also looking at what is the feedback. But our product teams have already done that, which is with the Watson, the feedback loop, if you will.
Right. So in Spark, as it is in open source, you have to specify each parameter value. So.
I got it, but my point is that you could.
Yeah.
You could walk through and you could say, well, programmatically, just change how big and how many different layers you had. And, I wouldn't have to sit there and do it over and over. You could actually just pull back and say, well, how well did the. Here's my limit to how many.
I think let's talk offline. I just want to end the session so everyone feels free to this thing. But, thank you.
Thanks.